the quiz. Are you posting a video on?
Yes, I'll post a video quiz. Do you have any questions right now, though?
Yes, sir. For the two different E2 elimination products. Can't hear you. For the question number 3, for the E2 elimination.
Question number 3.
Yes, sir.
Which one can give 2 different ones? I think it's D, isn't it?
Yes, sir.
D? Yeah. The other compounds can only each give 1.
Yes, sir.
A, you can beta eliminate on either side, but either side gives the same exact product if you draw it out. So with these reactions, like the second one under 1, what type of reaction was that? 1B, if they're labeled with letters. What type of mechanism? Substitution? Which mechanism? SN2, yeah? With inversion? How do you know it's SN2 with inversion? Why not E2? You can't do E2 with that reaction. There's no beta hydrogen, yes. Basically, you need to assess your reactions. There's a number of things we talked about for assessing your reaction. Okay, with alkenes, you don't have to do so much assessment. With alkenes, I included a lot of stereochemistry. Here you have to do more assessment. What reaction is going to take place? Okay, and just because the quiz, I said it was over elimination, well, you get to the test, it's over elimination and substitution. You get to the final exam, and then you say, well, it can be elimination, substitution, addition, reaction, it's everything. So you got to be able to think more openly. Okay, and assess reactions. One last thing I'll show you. There are these diagrams out there available that sort of tell you what to do. Determining major reaction type, substitution, beta elimination. Question 1, is there an sp3 carbon with a leaving group? Like a halide or a sulfonate ester, which is tosylate. Is there an sp3 carbon with a leaving group? If the answer is no, guess what? You're not doing any of these reactions, right? Because all 4, E1, E2, SN1, SN2, all 4 of those require a tetrahedral carbon with a leaving group, right? All right. So if it does have a leaving group, then you can do them. Then you might ask, well, is there a beta hydrogen? Because if there's no beta hydrogen, you're not doing E1 or E2, right? Like we just said on that example. If there is a beta hydrogen, well, guess what? All 4 are still possible. Is there a beta hydrogen that's coplanar with the leaving group? But you got to be careful, because I would have said, is there a beta hydrogen that can become coplanar? Because you can rotate, right? If no, then you can't do E2. Now note that it doesn't say trans or syn, because trans is preferred, but syn coplanar does work. It's just much more difficult. If yes, then everything is still possible. Is there a very strong base? On down the line. And you can get, we've covered most of this. Leaving group on tertiary carbon. If it is, what type of mechanism is possible? SN1 or E1, because the leaving groups on tertiary carbon, you don't do SN2. How do we get rid of E2 here? But you could do E2. Somehow we must have gotten rid of E2, I don't know. Anyhow, solvent. I did protic, aprotic. I didn't do protic, aprotic. I did polar, nonpolar. Anyhow, such is available out there, but most of this we covered. I could send you that if you wanted, but the problem with that is you guys are going to tend to want to memorize that stuff. And I'll send that to you if you'd like to take a look at it. Really more to confirm what you know. Any last questions? Yes.
For syncoplanar, can you ever get a Satan product if your hydrogen, the beta hydrogen in your leaving group are syncoplanar?
Syncoplanar does work. It worked. You did it in lab. If you made an alkyne in lab, W2 elimination. The second elimination is syncoplanar because you're starting bromide, etc. Or was it? I'd have to think about it because the starting dibromide is miso, wasn't it? Yeah, I have to think about that. I'll take that back. Syncoplanar is possible, but it's more difficult. If you can do an anticoplanar, that's going to take place first. If you cannot do anticoplanar, syncoplanar is possible, which is much more difficult. Is there a particular example you're looking at?
No, I was just wondering, because I think it was, I just wasn't sure if syncoplanar could ever give a Satan product, or if that only happened if your leaving group and beta carbon were anticoplanar.
I'm not quite understanding the question. I don't know why a syncoplanar could not give us 8-2,
Okay.
unless I'm missing something. They're not really related too much.
Okay, I think that's, yeah.
I'd have to look at a closer example. Maybe you're seeing something that I'm not thinking about. Okay, did I pass out the radical? No, I didn't. Please take one. It's one handout. The very bottom of this diagram here, somehow it eliminated SN2E2. Then the final question here looks like heat. Are you heating? If yes, what reaction are you going to get? E1. Didn't we say heat favors elimination? Yeah. You're not heating, more likely to be substitution. That's the way this says here. This particular diagram does bring in a couple of things we did not talk about. That is base, strong or very strong. See, I didn't distinguish between strong and very strong, but they're doing it here. But I did sort of say this. I said the stronger the base, the more it's prone to do elimination, right? Better the nucleophile, more prone to do substitution. Yeah. Stronger the base, you're going to get E2. Strong base, they're sort of saying, it can be either. But if it's very strong, you're going to get elimination. Of course, if it can be either, how do you decide? Well, then you say maybe it's the base or substrate crowded. Because if it's sterically hindered, which one's that going to favor? Yes, you go to E2. If not, then still both are possible. In some cases, you may have a reaction where both are possible. You may get mixed products. You may get both a substitution and elimination product. Or there may be Well, yeah. In a testing format, maybe you're given some more information to help you decide. But there are some reactions where both substitution and elimination are equally as possible, and you're going to get a mixture. Although you can always start heating it. Higher heat may favor the elimination product. So there's hopefully something that can help you narrow down what your product's going to be, typically your major product. Okay, any last questions? I'm going to turn the light back on, yeah? So we'll have lab this afternoon, we'll meet upstairs, we'll check out, then we'll go downstairs for lecture on UV Viz, and we'll have a little bit of review time. Okay, at this point, if there's no more questions, I'll begin some new material, which will not be on test 3. And that is the radical bromination of alkanes. This will be on the final exam, though. Okay, can you do chemistry with simple alkanes? Like this here. What have we done chemistry with? Mainly we've done chemistry with the first reaction with alkenes. Because alkenes have the pi bond. The pi bond is reactive. It can act as a nucleophile. Those electrons are held loosely. They can react. We also did very similar reactions with alkynes. Those were twice the fun. Then we went on to dienes. Well, that's just alkenes, but also twice the fun, the diene. But those have unique reactions because of conjugation. You can also do Diels-Alder with a diene. Then we got to leaving group chemistry. All right? Well, with leaving group chemistry, you got two main components. Either one could be large organics. The substrate tetrahedrocarbon with a leaving group, that's one component. That would be the electrophile. Then the other would be the nucleophile. And the nucleophile typically is something with a lone pair, yeah? Okay. Well, look at an alkane. There's no alkene, so it can't react with alkene reactions. There's no leaving group, so it can't be the electrophile in those type of reactions. And there's no lone pair, so it can't be a nucleophile in the leaving group chemistry reactions. So what can it do? Early on, I showed you that you can burn it, combust it, and heat your grill and cook your hamburgers. And it was at the bottom of one page on an early handout. The second, though, was a radical halogenation. And that's what we're covering now. And back then I told you we would cover it at the end of the course. And here we go. Other than burning alkanes to heat your grill or your house, the other most common reaction is radical halogenation. And more specifically, it tends to be radical bromination. Because with bromination, it works out, you can get a good yield because of the thermodynamics. With chlorination, other halogens, it's more difficult, the yields are not as good, etc. Bromination tends to be more selective and higher yielding. An example reaction, if you take this alkane and we're reacting it with elemental halogen, bromine, in the presence of light, H nu, or heat, or peroxides, you can get a reaction and you can end up with a bromine now bonding to your alkane. This is a substitution reaction. Because what have we done here? We've replaced this hydrogen with a bromine. That's substitution. So it's not addition. We didn't just add bromine. We didn't eliminate anything. we substitute. Okay? But it's not an SN1 or SN2 because there's no leaving group here and there's no nucleophile. But it is a substitution reaction. By the way, what else is going to be formed here in this reaction if we balance it out? HBr. Yes, that's the fate of the H and the other bromine. It will form HBr. Okay? If you do this reaction, it'll start giving off a gas. You can actually see it because it'll be vapor. And if you hold pH paper on it, it'll turn it red. It's HBr. Okay. At what position did we add the bromine? I say add, it sounds like an addition. Okay, overall it's a substitution, but at what position was the bromine added? Is there any terminology we can use? Tertiary. Added that, okay. We brominated at the tertiary carbon, right? And this reaction is usually very regioselective for the tertiary site, for that region of the starting material. Now, if you do chlorination, it's less selective. You're going to end up with chlorine on just about any of the carbons. And we'll mention later maybe why. Bromination tends to be regioselective, and thus you can get a high yield of a single product, and not just a complex mixture of different regioisomers. All right? Now that mechanism is a radical mechanism. We'll look at it. But before we do, let's compare it to this reaction. Alkene. And how do alkenes react with bromine? Addition. You did this reaction in lab with transtylbene. And we would expect the product shown here, yeah? A dibromide with nothing else formed. And there we added bromine to the alkene. It's an addition, yeah? Now this reaction is very easy. The pi electrons are much more reactive here, and they're going to react, and you can do this room temperature. You can even do it in the dark. Cold temperature also works. I don't know how cold. You can't go to absolute zero. It ain't going to react there. But sometimes brominations are done cold for some reason. Sometimes they're done in the dark. You know, sometimes you turn the light off in the lab and for certain reasons. Up here, this requires some energy input. Light is a type of energy. Heat is a type of energy. Or peroxide. Peroxide is not really a type of energy, but it can make the reaction, promote radicals. This down here is what type of mechanism? It's not a radical mechanism. It's, like most of the mechanisms we've done, an ionic mechanism. That means that the intermediates are ions. What's the main intermediate in the reaction down here? There's actually only one intermediate. What's the name of it? No, there's no carbocation down there. There's only one intermediate in this reaction. What's the name of it?
Back bonds?
Well, that's not the name of an intermediate. It sounds like a process.
Okay, she said.
Bromination?
Yes, thank you. Yes. Bromonium ion, right? They came from back bonding. You can envision a carbocation, but it's not really formed because the back bonding occurs at the same time. Bromonium ion, and then, okay? Final exam is in like about 10 days. But it's an ion, okay? And thus we call it an ionic mechanism because it involves ions. All right? The reaction above is a radical mechanism, okay? That implies what? The intermediates are radicals. Okay. Now, what is a radical? It's not some 1960s long-haired bandana wearing hippie. All right. What is a radical? It's something that has a single unpaired electron. Okay. Let's look at the mechanism for the radical bromination up top. Okay, the first thing is, well, the bromine. With bromine with heat or light, H nu, okay? Now we sometimes do this type of reaction in the lab and we actually pull out a lamp with a light bulb and we shine a light on it, okay? Your halogen bonds are kind of weak. You can look at bond strength tables. This will cause this bond to rupture homolytically. Homolytic. One electron will go this way and one electron will go this way. And when we move a single electron, we use a Fisher carrier. Okay? So there's 3 lone pairs. What does this give? It's now going to give a bromine with 3 lone pairs. But what else is here? Just 1 electron. And then what do we produce on the other side? Same thing. So can I just say 2 of those? And so the heat or light energy, okay, heat or light, you got a light bulb, and the energy comes in there, okay, and it causes this. Homolytic. What is homolytic? Well, lytic means lysis or cleavage. What's homo? Okay. It's because each atom got the same thing. Each atom got 1 electron. On the other hand, if you take HBr and maybe put it in water, what will happen? Both electrons will go to bromine, and the H will be left with what? Nothing. So, and it'll be ions, because H has nothing, it's plus. The bromine has the lone pairs, but now it's got another lone pair, and that's minus. It's ionization, but it's also called heterolytic bond cleavage, because it was different. One atom got 2 electrons, the other one got none. So this is homolytic bond cleavage. Because there's no polarity here. Why would you give both to bromine and none to the other bromine? So it just splits equally. Okay? The weak bond is broken by some energy input. You get bromine radicals. I don't know why this is not right. Lighting. Bromine radical. Okay. I'm going to pull this down. These bromine radicals, once formed, will be reactive. Okay? And what they will do, we got this H here, right? It will, I'll use a very scientific term here, it will strip one of these H's out. Okay? How do we show this? 1 electron here will move, and one of these electrons will move, and they'll team up. But the other electron in this covalent bond moves here onto the carbon, or just remains on the carbon. And what does this electron movement give? Now you can draw this or whatever back down here into this space. What does this look like? This electron teams up with an H electron. What are we making here? We're making HBr. And what are we leaving on this carbon here? A single electron. So that's going to give single electron here, because 1 went on to carbon, And then we made plus what? Plus HBr. Because we showed a bromine electron teaming up with an H electron. They teamed up to make a covalent bond, that's HBr. And we said we were going to make that, yeah? That's the gas that we said we were going to make. Okay, there that is. How do we get the final product? The organic product. We made two radicals. This could these two could team up, and that would give product. You can draw that to product. Would be done, right? That look like a reasonable mechanism? Question?
I think you're gonna answer it.
Well, tell me, because I mean.
Well, because you keep saying this could, so it sounds like this is really not what happens. But it also sounded like you were about to go ahead and go into it, so I'm sorry I jumped in. You can go ahead.
So you know how I talk. Yes, this could happen, but that ain't the mechanism. You gotta be careful with my X. Yes, that would give the product. My X means that ain't the root. Because there's something we know about this reaction. And information that you know has to fit your mechanism. It's like stereochemistry. If you know the product is racemic, then your mechanism should show why it's racemic. What we know about this reaction is the light, you only need to shine it at the beginning. First couple of seconds. Then the reaction will proceed. You can turn the light off and the reaction will keep going. It'll just keep going and HBr will keep being eliminated. But we turn the light off. Well, then you can say, well, do we need the light at all? And the answer is yes, because if you don't turn the light on at all, it never starts. So essentially, you can turn the light on for a little bit, get it going, and then turn the light off. Well, if we do the mechanism that we just showed here, we just made one molecule, a product. How do we make the next molecule? Because typically you're going to make a gazillion molecules if you're going to be able to see the product. So that's one. How would we then make the second one? Wouldn't you have to have this happen again? Well, this requires light or heat, but I'm focusing on just one of them. So you'd have to do this again. And then you make another molecule, and then how do you make the third one? You'd have to do this again. It requires light. But I'm telling you, you can turn the light off and it'll keep going. So how does it keep going? The answer is, this doesn't react with the other bromine radical. If it did, that would be a termination step. And termination means that you've got to start all over. And you've got to come back here and you need light again. What we need is a propagation. We need something where we get this self-sustaining cycle. And that's common to radical reaction. Instead of that, this reacts, we bring in the second bromine here. I'm going to get rid of this. And instead of reacting with that, we react here. One electron comes here, and one of these comes here. This teams up with the bromine radical, and this goes here. And what does all this give? Well, first off, when these team up, we get what? Product, and you can draw that to product. But what do we produce? We produce a bromine radical. And if we do it this way, now this can come back over here, and it'll be a bromine radical to do this. Now we have a cycle, and now we can turn the light off because we no longer need to produce bromine radicals this way. Now we have a reaction that produces bromine radicals, and it can come back and do this, which came from up there. And then when it does this, and you produce a bromine radical, and now it just cycles a gazillion times. And you can turn the light off. Because we no longer need to make bromine radicals this way. We have a mechanism that generates bromine radicals. Question?
Could you use the same radical, cyclic radical nature for a battery for the transfer of electrons like that?
I'd really have to think about that. I'm not used to thinking like that. And we only have 5 minutes. Things like that. But it sounds like, I mean, you know, it's a cyclic propagation. Yeah. I mean, these types of things are applied in many cases, yeah. Okay, you see the difference? We generate bromine radicals and it can self-sustain. That's called propagation. Okay? Is it an A, propagation? Or is it an O, propagation? Okay, termination, propagation is what we want. We can turn the light off. So that's how we would do it. And that's a radical bromination, and this is a well-known reaction. It can be done in good yield. Why the tertiary carbon? Why is it regioselective for tertiary carbon? Where did we made here. We could have stripped an H out here and made a radical there. Why is this radical better? Well, tertiary. What's better about that? Well, a radical is just like a carbocation in the fact that it's electron poor. Does the carbon have an octet here? No. 2, 4, 6, it's only got 7 electrons. So it's electron deficient. Now it's neutral. There's no charge here. The charge is neutral. It owns 1, 2, 3, 4. But it is electron poor. And since it's electron poor, it's stabilized just like carbocations. Where's the best place to make the carbocation? Tertiary, because of inductive donation. Same for radical. It's the best place to make radical. And so the transition state leading to this radical is going to be lower than the transition state leading to some other radical. And so this is the one you get. With bromine, if you were doing chlorination or fluorination, it's not as selective because it's so exothermic. It's sort of like a hurricane. If water's running down the road and you've got 2 roads, the water goes down the hill, right? Like when regular rain. But what if a hurricane came and it was like a huge amount of water? You might see water going up the hill because it's just so much. You lose the selectivity when it's so much energy. So you lose the selectivity with chlorination and fluorination, and so that you tend to get mixtures of products. Radicals forming non-selectively. Iodine, on the other hand, this is a hard reaction to do because iodine is more unreactive. And actually, this reaction can be reversed. And we'll talk about the reverse later. But the reverse would be what? Taking this alkyl bromide and going back and forming bromine. Okay, but that would be the reverse. And that's more prone with iodine compounds. Because in fact, if you buy a compound like this, if you buy that compound, after a few months or a few years, it'll start turning brown. That's because it's going backwards. And doing this, and the H is likely coming from maybe water in the air or something. But it's producing iodine, which is brown orange. Okay, going backwards. We'll talk a little bit more about that on one of the next pages. And on Wednesday, yeah? Let's finish up a little bit here. Can you show product of this reaction here? This is with light. You can also do, this is peroxide, okay? Light or heat. Peroxide, I'm not going to show mechanism, but the peroxides help form bromine peroxides, or bromine radicals, instead of light. Mainly because peroxides easily form radicals, and when they form radicals, it helps the bromine form radicals. Okay, I'm not going to go into it, but you can do this reaction using peroxides. We need to finish up here. Let's see. So, what I want you to do is please look and try to answer some of these questions here in preparation for next Wednesday. Question below. And then the back page is looking at the reversal of the reaction, like I showed here. But it's a very important application towards the ozone depletion. Okay? There's also a unique mechanism down there, which again, well, Michael Faraday did that reaction down there. I think he also invented electromagnetism. Test on Monday. See some of you this afternoon. We'll finish this handout out on Wednesday.